to you a bit more about the EEG data that we have. And as was mentioned before, we have data from roughly 1,000 participants. They all came to the clinics 4 times for 4 assessments. And there were 20 minutes of EEG recorded at every visit. For this, we used 126 EEG channel configuration, which you can see schematically how this would look like, electrode placement on the head in the bottom left. And the recording sampling frequency was 5,000 Hz. Why am I telling you this? The story is simple. We have a lot of data. In the middle, I'm showing you a chunk of EEG signal, just for an example how this would look like. This is just a single second of EEG, only showing 21 channels, and the sampling frequency here is just 120 Hz. So it's considerably lower in terms of amount, and already it's quite messy and very difficult to understand what's going on. So what are these EEG signals? They are compositions of oscillations at different frequencies and with different strength. And what we are trying to do to make sense of what this brain activity is, we try to decompose it. You can see this to the right. So we're trying to estimate from these signals how strong are the different frequency components within that signal. And this is what we then call the EEG power. And if we do it for the entire frequency spectrum, we will obtain power spectral densities. So this is one of the major factors that we are interested in the EEG. A second one, is the connectivity, although I will not go too much into detail here, but we are also interested in how do 2 signals oscillate, or how in sync are they, signals from different brain areas, and this will give us measures of connectivity, like how strongly do they correlate, and this is another interesting property of the signal that we are looking into, but it's not part of this talk here. To get to these points, to trying to make sense of this brain activity, we need to go through a couple of steps that are all pretty involved. So for one, we need to detect, reject, or repair bad channels. Bad channels can occur probably during recording because there was a disconnect, or because the gel was going dry, or problems like that. We have to filter the EEG signals, both low pass and high pass, to remove noise from the signals, and we apply a notch filtering to remove the line frequency noise, which is 50 Hz here in the EU. Furthermore, we split the EEG up into different chunks that we call epoch, and then we also try to detect and reflect or repair these epochs. If they are too damaged, then we need to reject them because the data cannot be used for further analysis. Generally speaking, we just want to separate the brain activity from all kinds of other activity, noise in general, and we also can do this through a technique called independent component analysis. This lets you separate the different sources, and there we can then see these are probably eye blinks, this is muscle activity, this is movement, and then we remove that from the brain activity to continue with our analysis. This is now actual EEG data from the ARMN study. You can see the visits on the x-axis for visits, and you can see the different sides on the y-axis, Helsinki, Madrid, Oslo, and Rome. And we have 2 recording conditions, which you can see in the solid on a dashed line, being eyes closed and eyes open. What you can see here is that you have generally higher power in the eyes closed compared to the eyes open condition, especially around the 8 to 12 Hz frequency range, and this is very expected, and it's very good that we see that. But looking at this data from this point of view, it's again very hard to interpret anything. Differences are small, we don't really see what's going on. So this is why we are looking at it from another angle. To the left you can see the same figure as before, but just a visit 1 and collapsed into one single side basically. This is the average across all the sides. And then we are interested in the change of the EEG power relative to this baseline activity. So obviously at visit 1 the change to baseline is 0, but afterwards things look like this. And it's quite interesting to see that both in eyes closed and eyes open states, you can see that the EEG power is dropping relative to the baseline throughout the course of the study, throughout these 2 years. Which could be an indicator of some cognitive declines going on. And then the second thing that we're interested in is also the difference between these 2 different recording states in EEG power. You can see this at the bottom here. Again, across all the sides average, and then again relative to baseline. And also here you can see, this is a bit more chaotic, the changes here, but you can also see here in this central region around 8 to 12 Hz that there is a drop in the power. This is a bit more complicated now because it's a double difference. So the difference between eyes closed and the difference in time to baseline. And there's people here among the speakers that can better explain the biology behind it. But effectively, it means that the difference between these two states in power gets smaller throughout the time. And this could also be an indicator that some cognitive decline is going on in these participants. Christopher mentioned it. We are also very interested in trying to figure out the effects of age also on the EEG, which is a big challenge. You can see here again power spectral densities across all the sides in different age bins from 60 to 80 years of the participants at the time of enrollment. And I just want to draw your attention to these very high frequency ranges here because there can be seen the best. We do have a systematic difference in these EEG power spectral densities that correlate with the age. And now the very big challenge is, of course, which of these changes are naturally due to natural aging and which of them are related to cognitive decline or to developing dementia. Disentangling that is very challenging, and that's what we are trying to do. Right here I show you now the outcome of one analysis, although it's preliminary. It's a baseline analysis. And we are trying, with the generalized linear model, we try to explain a variable that we derive from the Cambridge Neuropsychological Test Automated Battery. So one way of expressing cognition in our study. And we're doing so by using several variables. For example, the site, age, the p-tau biomarker, p-tau is 217, the ApoE4 alleles, some EEG variables, education, and the sex. And we can see a couple of very interesting things here. For example, we have significant differences between the different sites. So Oslo is the reference here, and in Rome, if you come from Rome, then you have a significantly lower cognitive score recalling to these countermeasures that we're using here. The same holds for Madrid, while Helsinki is not significantly different from Oslo. Similarly for age, if you have high age, then also your cognitive scores are considerably worse. On the contrary, if you have high education, then you have a very good or very high cognitive score. And being male actually also is substantially or significantly higher in the cognitive scores. Although this might rather be correlated to age and education, I would guess, because thinking about our population again, participants are between 60 and 80 years old. Going back in time, probably it was just not very common at the time that females did have very high education or were allowed to have very high education. Another thing that is very interesting to see is here that if our model has access to the p-tau biomarker, which is significant, so if you have high levels of p-tau 217, your cognitive score is low. The model does not require the information that comes from the ApoE4 alleles, so it prefers the p-tau measures over the ApoE4 status, which are very closely correlated, as Christopher has shown before in this course. And in this analysis now, our variable that we derive from the EEG, it actually is not significantly contributing to explaining the cognition. However, we believe that this is just one way of doing it, and there's plenty of ways of defining this variable and this variable, so this is just one very preliminary test. We are very convinced that we can find interesting correlations there, and also if we include now the other visits. As I said, this is just a baseline analysis. So more important or more interesting things are waiting to be analyzed. And now on the actual potential of AI in what we are doing in cognitive healthcare. Actually, it can be beneficial in all the stages, intermediate stages that I've mentioned to you. So although it was not done for the Gemein study, it's very likely that in the future AI-based techniques will be used to actually gather data. For example, think of all the ChatGPT chatbots and the likes. They can be used to gather patient data, for example, anamnesis, and automatically put them in a data format that can be used efficiently. Furthermore, I talked about the processing, like the cleaning of the data. And of course, this is an automated process within AI already, but there are still manual interventions needed, and AI could also help there to even facilitate this more. Then I showed you how we extract the power spectral densities and the connectivity measures. And there are methods, AI methods, for example, one that I'm showing to the bottom here, the artificial neural network, then can automatically extract relevant information from the data themselves, so that this step would be automated as well. And then, of course, when we're coming to the actual prediction of what can we expect from the data, then all of the models will be interesting, because what I showed you before was just a linear model. These ones are all non-linear, and therefore can probably help to uncover hidden trends and get better at predicting what's going on. And this brings me to the potential in the cognitive healthcare, but also beyond. What do we expect from the AI? Actually, to detect abnormalities and to detect them earlier and more precisely than before. And it can help us to uncover hidden correlations and trends in the data that we have probably not thought of. And it lets us go from group analysis to individual risk prediction. And in general, just lets us process all that data, this mass of data, which is beyond the capacity of one individual human to analyze. And with that, I'm giving the word to the next speaker, Tim Hollis.